Planning is demonstrated in OpenNERO in the Tower of Hanoi environment. The Tower of Hanoi problem is defined as follows. There are 3 poles and there are 3 disks that are stacked on top of each other on the original pole, and the task is to move them from the original pole to the third pole, which is the target pole, and there are 2 rules to follow. Only one disk can be moved at a time, and a disk can only be stacked on top of another disk if that disk is larger than itself. There are 3 planning algorithms implemented in OpenNERO that can solve this problem. The first one, which is loaded here, is called problem reduction. With problem reduction, the eventual goal is broken into sub-goals that if those sub-goals are completed, then the eventual goal can be completed. In this case, the goal is to move 3 disks from pole 1 to pole 3, and applying one step of that algorithm gives us 3 sub-goals, which is first move 2 disks from pole 1 to pole 2, then move that large disk at the bottom from pole 1 to pole 3, and then move those 2 disks from pole 2 to pole 3. And if we do those 3 sub-goals, then the goal is going to be achieved. But moving 2 disks from pole 1 to pole 2 is not trivial. So it's another planning problem, and it can be solved recursively with the same algorithm. And that's exactly what problem reduction does. Looking at that sub-goal, which is highlighted right now, it can break it down into 3 additional sub-goals, which fortunately in this case are all trivial actions which can be carried out immediately without any further recursive calls. So once those 3 sub-goals turn green, which means that they can be achieved, then the first sub-goal is green, which means it has been done. And we will move to the second one, which is trivial, and the third one, again, can be solved in the same manner. And once all sub-goals are achieved, the first goal is achieved, and at this point, Steve can carry out this plan, which was computed, and then do the problem. Let's speed up a little bit. So at this point, the first sub-goal is solved. Now the third disk is moved, and now this is the second sub-goal. And the problem is solved. The second planning algorithm we're going to look at is called state space search. State space search works by starting from the initial state and then considering every possible action that can be taken in that state. For example, in this state, there are only 2 possible actions, which is to move the red disk either to the third pole or to the second pole. And in a DFS manner, from this resulting state, now state space search considers every action that can be taken in this state, and then this process follows until it eventually manages to see the end goal state in some combination of actions that it has taken, and then by following the actions that it has taken, it can know of a plan that will take it from the initial state to the end goal state. So it's basically an exhaustive search, but because in this problem the number of states is very limited, that's a viable solution. So we can speed up this process of this search, and as you can see, it's just backtracking sometimes because that path that it has taken doesn't lead to any new states, and then at some point it has discovered that from this state, by following these actions, it can get to that end goal, which is the desired state. And at this point it can again execute that plan and then solve the problem. We can speed up through this as well. and the problem is solved. The last planning algorithm we're going to look at is called goal stacking or strips planning. The way this works, it's somewhat similar to the problem reduction planner in that it breaks down a goal into sub-goals and tries to achieve those sub-goals first. The difference here is that with problem reduction, we use our domain knowledge to break down a goal into sub-goals. But with the goal stacking planner, the way it works is more general, so it can be applied with less domain knowledge. And the way this works is that it knows of a set of actions that can be taken. And each action is defined as a set of preconditions that need to be true for the action to be applicable, and the action, and a set of postconditions that will result once that action has been taken. And there's a special language used to define these conditions. For example, here in the initial state, this is the initial state, just the two disks on top of pole 1, and this is that state described in this language. It says disk 1 is on top of disk 2 is on top of pole 1, pole 2 is clear because there's nothing on it, disk 1 is clear because there's nothing on top of it, and so on. So in this language, in a similar manner, the goal can be defined as two components. We would like disk 1 to be on top of disk 2, and we would like disk 2 to be on top of pole 3, which is the target pole. So let's see how this algorithm tries to solve this. So the first goal is already satisfied because disk 1 is on top of disk 2. But the second goal, which says disk 2 needs to be on top of pole 3, has to be somehow satisfied by taking some actions. So the way the algorithm works, it considers every action possible that can take disk 2 to pole 3 from anywhere it could be, and it assumes that they are all satisfiable, they're all applicable, and then tries to satisfy their preconditions recursively. So here you can see that there are 3 actions selected. All of them are moving disk 2 to pole 3, disk 2 to pole 3, disk 2 to pole 3, but they have different originating poles. The first one says move it from pole 1, the second one says move it from on top of disk 1, and the third one says move it from pole 2. So recursively, it tries to satisfy the preconditions of these actions in a DFS manner, and if it fails, it backtracks and goes on to the other action. And at some point, if it can achieve all the preconditions, then it considers the problem solved. So let's see how we can satisfy the preconditions of this action. So to move that to move disk 2 from pole 1 to pole 3, these are the preconditions that need to be there. First of all, disk 2 has to be clear, meaning that there's nothing on top of it. Then disk 2 needs to be on pole 1 because we're moving it from pole 1, and pole 3 needs to be clear because that's the target. So in order to have disk 1 clear, again, we need to do something, and these are all the possible actions that have clear disk 2 listed in their post conditions. So this algorithm again goes through all these actions and just tries recursively to get one of them to be workable, and then this process is continued until at some point we can achieve both components of the goal. So we can just skip the rest and just go through this more quickly, and then somehow it managed to satisfy those components, and then if we execute the plan, we will see that it's been able to carry out this problem. So this is a simpler version because it has only 2 disks, and the reason why is that if we run this on the 3-disk problem, the algorithm can be caught in an infinite loop, and that is actually an exercise for you to change the goal stacking algorithm so that the infinite loop case doesn't happen. So we have looked at 3 different planning algorithms in OpenNERO, and that was planning in OpenNERO.